Yeah, we are live now. Hello everyone. Just a sec. Give me a few minutes so that I can handle the thing. Yeah, okay. So here we are. Sorry for the delay. There was this slight glitch in this setting. I was not aware, so I'm sorry. Let us begin with the thing. Those of you who joined, just let me know whether I am audible properly. In the chat, you just let me know that I'm audible, and yeah, very good morning. So let me know in the chat whether I am audible, and then we begin. And I'm sorry, I'm little down on health, so I'll just quickly complete the main part that we have to discuss, and we will go for the uh, important things that are there. Yeah, I am audible. Thank you. I'm audible, and let us go for the main part. Now, today, my topic that I want to discuss with you on eigenvalue and eigenvector, before even taking you to the solving of the questions, the main thing is here that we are going to see a advanced notion, that is algebraic multiplicity and geometric multiplicity, as I had already said you. So this is the concept, algebraic multiplicity of an eigenvalue. Now this is very easy part, but geometric multiplicity is slightly twisted version. So we say here, let a n cross n, okay, be a matrix with eigenvalue lambda 1, lambda 2, lambda n. Then algebraic multiplicity of a particular eigenvalue lambda I is defined as the number of times that eigenvalue is repeated. Now this is the meaning over here. Okay, now this is a very simple and a very easy definition. It is straightforward, visible from the what you call the, when you find the eigenvalue, it is very much visible. You don't have to think too much. It is only just the name given to the number of times a particular eigenvalue is repeated. Now we will see this in with the help of an example. In the initial part I'll give you the main theory, and now let us go for what is called a geometric multiplicity. Okay, now this is the thing which is very crucial here, so I'll just write here in blue, geometric multiplicity of an eigenvalue. Now this part is not clearly visible when you calculate I'm sorry. This part, when you calculate geometric multiplicity, you have to be little careful while doing this, because it leads you to different conclusions from the calculations, and what all differences are there you come to know from geometric multiplicity also. So again here the same thing, let a n cross n be a matrix with lambda 1, lambda 2 up to lambda n as the eigenvalues, then geometric multiplicity of a particular eigenvalue is defined as, or we can say geometric multiplicity of a particular eigenvalue lambda I. That would be a great thing. Lambda I is defined as the number, as the defined as the number n minus rank of a minus lambda I. Okay, this is there. So it is sometimes it is n minus r also sometimes we write, but we will see with an example. You can keep a note over here. You can write a note. It also is, it is essentially number of free variables. You can just essentially it is number of free variables. Now there is something more also, kernel and all etc. These things are also there, so you can check that, and you can try to do that also. But right now I won't enter into kernel and etc. because that's not the time of discussion now, but I just gave you a hint, as you know, out of curiosity, like you can search all those stuff. Just let me do a bit of more setting properly, and yeah, we would be done. Now when I tried to stream, but then there was some glitch then, so the thing did not work properly, so I'm just doing a bit of more setting. Yeah, so please give us a thumbs up. Do give a thumb up if you have written down the concept or you have followed the basic general definition. This is on this slide, there is too much of theory you can see right now, so just hit like if you have understood regarding this. In detail you will understand when I take an example about how what is geometric multiplicity and what is algebraic multiplicity. Okay, so now we go for another theory. Just hit like and I'll take you ahead in this. Are you able to follow? Okay, are you able to follow on this? Just let me know. Okay, fine, cool. Let us go ahead, and those of you are there, you'll like to understand more now. Let us see how to go about the next part. Now comes a very important definition. This definition I have already given you a version of it. Okay, in my previous live session I have shared a simple result and we had been able to do it. Now comes the main part of something called diagonalizable matrices, right? So that comes here, but now comes a very important part, something called as similar matrices. Similar matrices. So what is it? We say two matrices, capital A n cross n and capital B n cross n are said to be similar if there exist. Now in mathematics this word there exist is denoted by this symbol reverse of E. Okay, you write this way: if there exists a non-singular matrix capital P n cross n such that now this is the result, this is what comes here, such that A is equal to PB P inverse. This is the main definition. Now you can remember this part as the first original definition. This is what it means, that two matrices are similar. Sorry. So A equal to PBP inverse, this is what we have. Now on this we have another alternate version is also there, or you take this way, it is AP is equals to PB. Okay, then the next part is, or you can take something here is P inverse AP is equals to B. This you can take. Okay, P inverse AP is B. These are three variations in the definition. So this is what we have. Now here comes a very important result. The first result is result number 1 is if A and B are similar matrices, then they have same eigenvalues. Okay, in another words, it means that it also means this thing, that they have same characteristic equation. This is the another meaning here. Okay, now this result can be proven. I am not entering into proof of any result because none of the proof come in a very most of the exams they don't ask you to prove. The most of the time what you need to know is how to apply the statement, how to use the theorems in most of the engineering exam. For BSc there are rigorous proofs are there. So right now I'll keep the proof on hold. I'll just we'll digest the concept while solving and everything. Now we go for something called as similar matrices. We have seen, now we go for diagonalizable matrices. I hope you have written down the theory of this, and let me know. Oh, very good morning to all of you, uh, those who have joined. I'm right now catering on similar matrices. If you have any difficulty over here, then please let me know. So far we are just seeing the theory, so that's not an issue. I believe when we see solving of a problem, that time it will be slightly tricky, because all this theory is going to be put to use. So if you are done with all what I have shown you on this slide, you can let me know. Just let me know, I can continue, and then I'll go ahead. Are we fine? Are we doing great on this? Just let me know in the comment section, then we can go ahead. Are you able to handle this? This is just theory basically. Alright, I think yeah, yeah, fine. We have got yes, so let us proceed. A very good morning to all of you, those who are there, those who are joining. So we have good mornings coming at, yeah. Let us now move to something called as diagonalization, because see, diagonalization is a concept which is made from similarity. Okay, now we go for the original definition of diagonalization. So diagonalizable or diagonalizable matrices we say let A n cross n be a matrix. See, whenever you come to the word A n cross n, please remember in your mind. Oh, thank you Sanket for your request. Yeah, so please remember in mind A n cross n whenever you say, is that just a minute, you have to remember that it is a square matrix, because many children get confused. What does a n cross n mean? A n cross n means that it is a square matrix. Okay, so this must not become a problem whenever you read. It is just a precise language of mathematics to say that it is a square matrix, a n cross n. So nobody is going to bother afterwards again and again that a is a square matrix, they will just write a n cross n. Okay, so a n cross n be a matrix with eigenvalues lambda 1, lambda 2 up to lambda n. Okay, then we say that a is similar to a diagonal matrix D n cross n if there exists a non-singular matrix capital P n cross n such that A equal to P D P inverse. Okay, this is what is the definition of a diagonalizable matrix. Now here we write something where dn cross n is basically it is lambda 1 lambda 2 dot 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 in diagonal up to lambda n. So you have all zeros. So in mathematics, see, we don't write all zeros like this, we don't put like this all zeros. We generally in mathematics we write it like this. We write like this one. Yeah, we put a capital O here, capital O here. So that means all entries are zeros over there. Okay, so this is how this matrix is there, n cross n, and a capital P is x1 x2 dot 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 up to xn. Okay, it is where x1 x2 up to xn are the corresponding eigen vectors of lambda 1 lambda 2 up to lambda n. This is the original definition of diagonalizable matrix. Okay, so if you are comfortable on this, we can go ahead. Yeah, so this is lambda 1 lambda 2 corresponding eigenvectors of lambda 1 lambda 2 up to lambda n. This is the definition. Now you don't have to mug up these definitions. Okay, these are just guidelines how to solve the problem. Okay, you remember them properly, it is good thing, but these itself are guidelines how to solve the problem. Okay, that is why the definitions in mathematics are absolutely very precise. They don't like to write any notation anyhow. They won't give you anything anyhow. They are super precise definitions, super precise notations they would use. And we have to be very careful, because when we code also, like if your coding system or coding language is grammar sensitive, your your code won't run if you do not put proper codes. So in mathematics also it is very strict with notations. Maybe it changes from author to author, but they are up to precision. You need to be very precise, you need to be very brief also at the same time. So it's very much crucial in mathematics. Now this is diagonalizable matrix. Now see, we have one more result related to diagonal matrix. We'll write down. If you are done with this thing of diagonalizable matrix, please let me know. I can move ahead. Please comment in the comment section, those of you are there. I can get the thing, and then we can go ahead. Yeah, let me know if you are there, then we can go ahead and you can write what you feel, how it is working at your end. Those of you are there, let me know in the comment section if you are able to understand this. Yeah, done. Fine. Okay, yeah, fine, let's go ahead and we'll see the next important result. Now this definition is quite big definition to remember, right? But as we use, we will remember. Now we see a very important definition now, or it is something called, I personally call this, generally in mathematics it is used as a theorem. Okay, but then I like to call this theorem with a nice name. It is a theorem. It is basically characterization of diagonalizable characterization of a diagonalizable matrix. Now see, whenever we have some matrix which can be diagonalizable or something similar to this, it has a certain feature. What is that certain feature? We have to see all the time, and this certain feature is nothing but this certain feature that we see in that matrix is nothing but the feature of algebraic multiplicity and geometric multiplicity. So here it comes. Why it is a characterization? Because you will see that this feature is always there. Okay, definition is, yeah, that definition will be always there always, but this feature is a hidden feature of the matrix. That's why we have, as a mathematician, we have uh, uh, you know uh, uh, have fragmented it from it, and then we have got a good nice theorem about it. So the feature is like this. So yeah, we write here a matrix a matrix A n cross n with eigenvalues lambda 1, lambda 2 up to lambda n is diagonalizable if and only if and only if. Now this if and only if in mathematics is sometimes written as IFF, so you can also use that. If and only if the algebraic multiplicity multiplicity of each eigenvalue is same as its geometric multiplicity. That's it. This is the crucial thing. Okay, this is the main characterization. Now please underline this thing that is very important here, that is this algebraic multiplicity of each eigenvalue. Okay, of each eigenvalue is same as the geometric multiplicity of each eigenvalue. This is the thing which will save us and which will help us from all the loopholes during the question. Now we write one result here which I believe, I guess I had given. If not, we'll have here one result, and then we are ready to go for a problem. Result number 1 is if a n cross n has all eigenvalues that are distinct, okay, that are distinct, then a n cross n is said to be diagonalizable. It also means here that sorry, I got a bit cold and cough from past 2-3 days, so I'm down on health. I'm extremely sorry, but I had scheduled this live, so I had to conduct it. So if a n cross n has all eigenvalues that are distinct and a n cross n, then we say that a n cross n is diagonalizable. There is a hidden meaning in this. Please write down that the hidden meaning here is that algebraic multiplicity of each eigenvalue is 1, then A is diagonalizable. This is a hidden meaning in the statement. This you have to understand, and then we can do it. Okay, now we are almost there. Let us see now examples. Lot of theory has been written so far, and we'll now go for the example. Okay, if you are done, if you are there from the beginning, please hit like. I hope this will help my live chat to go up, and please hit like, and we will see how to handle it. Those of you who are there live, let me know you have followed and you have written down the stuff, and or you can take a screenshot of it. This will surely benefit you. are you all there, or how shall we continue now? we because this is all the theory regarding the eigenvalues that we had to be doing. So yeah, we have got done. Yeah, hit like and we will shall go ahead. Yeah, so let us go ahead now. And this is the characterization. Okay, this all theory is extremely important. Now there is one or two theory I'll explain you during the what you call the example, as and when we will need it. So let us take up some example. So the question will come in most of the examination. There are versions of the questions asked, and I'll just take one big, make it a big question, and we will solve that. So let us take up a question, something similar like this. mm, I would like to go for a question in which something nice eigenvalues are available. Okay, I'll take up this, like first we'll take something with distinct eigenvalues, then we will do with the repeated eigenvalues. So yeah, let us take up this one. Yeah, this sounds good. For matrix A, let us take this example: 7 0 minus 2 0 5 minus 2. Then here it is minus 2 minus 2 and 6. Hopefully, yeah. So this is the example, and what are we asked to do is the first part. The first part here we say that find its eigenvalue and eigenvector. Second part is show that the matrix A is diagonalizable. Third part is if rather it is find the transforming matrix and the diagonal matrix of A. This is how, these are the portions in the questions that you will be asked, and in most of the examination the question comes like this. This is how they will ask you the question: show that A is similar to a diagonal matrix and find its diagonal form. This is what they have been asking in most of the examinations. Now such a question generally comes in exam for 8 marks. Okay, maybe it, if the question is small or easy, then it may come for 6 marks, but generally such a question comes for 8 marks in examinations. So this is very easy question, okay? Don't get scared. If you are sharp at your calculations, nobody can take away your 8 marks unless you write wrong. So yeah, so we have yeah, there are people who are online. Okay, now what do we do in this? So step number 1 is we will go for the answer here, and so the first step is we write let ax equals to lambda x. Yeah, always remember that any eigenvalue eigenvector question that you begin, in order to find the eigenvalue and the eigenvectors, you must write this as the most important step. Let ax equals to lambda x, x not equal to 0. This is the guiding thing, okay? This guides you to the correct thing. Always remember, eigenvectors are non-zero eigenvector. They cannot be 0. Please remember this. This is the line that tells you again and again x is not equal to 0. Therefore, determinant a minus lambda I equals to 0. This is what we got. Now we write our matrix. How do we write the matrix here? So we have to remember that the matrix, when we formulate, okay, I'll write here itself, it is determinant. When you formulate this, you write the determinant notation outside. If you are comfortable writing with the absolute notation, then it is fine, but don't make mistake all the time, okay? So because I have seen when we go for paper corrections or when we evaluate the answers, many children make mistake when they have to write determinant, they put matrices notation. When the matrices notation is to be given, they put determinant. It really disrupts the entire mathematical concepts of notations. If you misuse notation, like if you are coding, if while writing a for loop, there is a pattern that you have to follow. You can't disrupt the pattern or something like that. So sorry. So just be very careful that don't disrupt the notation. Write it carefully. So what you do in this, you subtract lambda from the middle values, from the values on the diagonal. Okay, 7 minus lambda, 5 minus lambda, and 6 minus lambda over here, not the middle value, I mean the diagonal. So 0 minus 2 minus 2 minus 2 and minus 2. This is 0. Now we are in a position to write the characteristic equation. So let us write the characteristic equation here. Therefore, the formula, I am now mentioning the formula over here. It is lambda cube minus trace a lambda square plus m11 plus m22 plus m33 lambda minus determinant of a equal to 0. Now see, this formula is the most standard formula which I have been giving you. Don't use other versions. I don't know, somewhere some people have used S1, S2, S3. These are no sense in mathematics. There is nothing called S1, S2, S3. in while writing like this way. Okay, it doesn't give any clear picture to the evaluator what is S1, what is S2, what is S3. S1, S2, S3 are not standard names for the terms that we are using, so be very careful while using the formula also. So now the trace, what is the trace we have to calculate? So trace, let us see the matrix. The trace is 7, 5 and 6. So you have to take the total of the diagonal element, 7 plus 5 plus 6, so 12 and 6, 18. 18 is the trace. Okay, so that is what you have to do. Now M11, M11 means you have to delete the first row and the first column. So in your mind, or you can just do something like this: delete the first row and the first column, whatever is left, take the determinant of that and write the answer. So here we have, here we will get 5 6 are 30 minus of minus 2 into minus 2, so that is going to be 30 minus 4, that is 26. Okay, what will be M2? M2 will be nothing but the matrix that is obtained. You have to take the determinant of that matrix, which is obtained by deleting the second row and the second column. So delete second row, second column, you get 7 6 minus 2 minus 2. Can you get the answer? Can you tell me the M22? Can you tell me the answer on the chat? What will be M22? I'll open the chat there. Yeah. You can use the calculator in, if you all are allowed calculator, yeah, at your place. Yeah, 36 minus 42 minus 4, you got 38. We have answer 38 there, and then yeah, so here you have 38. What about M33? Can you tell me the answer for M33? For M33, what you need to do is delete the third row and the third column. Third row and the third column, when you delete, what do you get? 7 5 are 35. Are you comfortable with this? 35 is the answer that we get. Yeah, cool. So let us go ahead and write the next part. So here we have 35. Now calculate the determinant of this matrix in your calculator, or those of you know how to calculate it orally quickly, you can get the answer. Let me know how to do it. So what is the answer you get? Determinant of this will be, what is the determinant? What is the determinant? Can you calculate the determinant from your calculator? It must be 162, I believe. Check your answer. Yeah, absolutely correct, 162. Thank you. Thank you for the answer. It is 162. Okay, now let us quickly calculate 8. This is lambda square, and then on solving this, you have 26 plus 38 plus 35 is 99 lambda minus 162. Okay, can you now calculate the roots of this equation? In your calculator you must get 3 different answers. Check your answer. What are the roots, can you tell me? So, and here you are expected to write this is the characteristic equation. Okay, so calculate the roots of this. Do mention what you get the numbers in the chat, so we will come to know. Yeah, I'll wait for your answer. The answer should be yeah, 3, 9 and 6. We have got the answer from Hemant, that it is 3, 9 and 6. Others, can you just check that it is 3, 9 and 6? It is a correct answer. Are you all getting 3, 9 and 6? Absolutely fine. Let's just hit like and put a thumbs up in the chat, and then we can go ahead. Yeah, so you have your lambda as lambda 1 is 3, lambda 2 is 9, lambda 3 is 6. Okay, we got these 3 answers. Now they are distinct eigenvalues, so write down here eigenvalues are distinct. Now can you recall what did we say about distinct eigenvalues? Yeah, what did we say about distinct eigenvalues? We had told that whenever eigenvalues are distinct, whenever eigenvalues are distinct, what did we say? Just a few slides back we had mentioned something. We had mentioned that the matrix is diagonalizable. So immediately whenever you get the eigenvalues distinct, immediately write your eigenvalues are distinct, hence matrix capital A is diagonalizable. Yeah, absolutely correct. Thanks. Matrix A is diagonalizable. So what do we go now? Now see, this is one step we have already cleared. Now what they want is they had told us, the question said that show that the matrix A is diagonalizable. We have used the result and we have shown that the matrix is diagonalizable. Not a big deal. Now can you see, if you have been asked part A, the part B got, see, part A in the question asked us to find eigenvalue and the eigenvector. Okay, so but part B got cleared first. eigenvector अभी तक सारे निकाले नहीं हैं हमने, फिर भी पार्ट बी पहले सॉल्व हो गया, क्योंकि पार्ट बी में आइगन वैल्यू से ही आंसर आ जाता है. आइगन वैल्यू अगर डिस्टिंक्ट है तो हमारा आंसर हो गया, हमको बाकी कुछ करना ही नहीं पड़ेगा। तो इसलिए पार्ट बी में पहले आ गया, और आइगन वेक्टर अभी तक हमने ढूंढा नहीं है। तो ये याद रखना कि जब डायगोनलाइजेबल है, आइगन वैल्यू को देख के ही कंक्लूड हो जाता है, ज़्यादा डिफ़िकल्टी नहीं है, ठीक है। तो अब यहाँ पर आपको काफ़ी अच्छे से, अगर 8 मार्क्स का क्वेश्चन है तो 3 मार्क्स 4 मार्क्स यहीं पे मिल जाएंगे आपको। 3 मार्क्स तो मिल ही जाएंगे आपको। 2 मार्क आपके आइगन वैल्यूज़ निकालने के, 1 मार्क ये कंक्लूजन का, है ना, कि आपको रिजल्ट मालूम है। तो यहाँ से अब चालू होता है जर्नी टू फाइंड आइगन वेक्टर। लेट अस गो फॉर फाइंडिंग आइगन वेक्टर। नाउ राइट डाउन, नाउ टू फाइंड आइगन वेक्टर। आइगन वेक्टर किसके लिए ढूंढेंगे हम? सबसे पहले आइगन वेक्टर हम ढूंढेंगे लैम्डा 1 के लिए। आइगन वेक्टर फॉर लैम्डा 1 इक्वल टू 3। तो लैम्डा 1 के लिए जब आइगन वेक्टर ढूंढना है, in order to find the eigenvector for lambda 1, we will use this equation: a minus lambda 1 I capital X equal to 0. This 0 is a 0 vector, okay? So therefore a minus 3i into capital X is equal to 0. What does this mean is, you write one below the other, because here I don't have too much of space on writing. So I'm now shifting into the next slide. So you write one below other. That now we will be taking the matrix, and from the matrix we will subtract 3. Okay, from the diagonal we have to subtract 3. That is what we do here. So what do we get is 7 minus 3 will become 4, 0 minus 2. Diagonal entry was 5. Second diagonal means entry is 5. 8 to 2 is 5, so it will become 2 over here. And the next one is 6, so 6 will become 3, and rest other places minus 2. Here there is 0, and here there is minus 2. x1, x2, x3. This is what you get. Now because eigenvalues are distinct, we will use Cramer's rule to find the answer. Okay. So the Cramer's rule, right, we'll write here: by Cramer's rule. What do we get by Cramer's rule? Let us see. So Cramer's rule will give us, firstly you write x1, then write over x1 above you put a determinant notation. We need to write a 2 cross 2 determinant, x2 above and x3 above the determinant. Now see, what do we do here? This, whenever we are using Cramer's rule, always take first two rows as the main row from which I'm sorry, from which we are going to calculate our eigenvector. So we will be fixing the first two rows as the main two rows for calculation of eigenvector. Always take first two rows only till the time you don't get 0, 0 and 0. All three become 0, then there is a problem. Okay, there is this word of caution. Let me put this word of caution, that here. Caution. x1 upon 0 minus x2 upon 0, x3 upon 0 is not allowed. Not allowed, okay? Otherwise every time everything will become 0 only. This is the word of caution. So is not allowed. Not, I'll just make it, you know, not allowed. This is a big thing. It's a danger. I can put danger. Okay, please remember this. It is not allowed. If this comes, you are in a danger, so you have to change it. So caution is that you must not get 0 0 like this. One of the two can be 0, two of them can be 0, all three cannot be 0. Okay. क्या कर सकते हैं ना, अभी मेथड में ऐसा गड़बड़ है. सी क्रेमर्स रूल इज वेरी वेरी इजी मेथड, बट देर इज दिस कॉशन में सारे बच्चे फंस जाते हैं. ये मैट्रिक्स ऐसा गड़बड़ वाला आता है. मैट्रिक्स को देख के, जस्ट बाय लुकिंग एट द मैट्रिक्स, नो बडी ऑन द प्लानट अर्थ कैन टेल यू व्हाट इज द whether the matrix is diagonalizable or anything. It is not possible. You just can't gaze at the matrix and tell, oh, it is going to happen, it is not going to happen, because matrix eigenvalues, by name itself it is suggesting the eigenvalues are hidden characteristics, hidden features they are. So you cannot just get or think, okay ये बन जाएगा. You have to understand it. And Cramer's rule में थोड़ा गड़बड़ी है, थोड़ा एक ट्विस्ट है. तो ये ट्विस्ट ये है, एक ट्विस्ट ये है. तो इसके लिए आपको हमेशा ध्यान रखना है. Please remember this, that the first two rows you choose. Now let us do this. Now how to write Cramer's rule? Okay, when you are writing for x1, you can just put small x1 over here, small x2 here, small, just for our reference. Don't do this in exam or anything. It is just for our reference. So for x1, what you do, you delete the first row, first column, sorry. You delete the first column. So if you delete the first column, and we have already fixed the first two rows, right? So in the first two fixed rows, what do you get? You get 0, -2, -2, -2. Okay, this is what you get. Then when you have remember, another word of caution is that x2 is always with minus sign. ये गड़बड़ी नहीं करने का. हाँ, x2 हमेशा माइनस साइन के साथ रहता है. मैनी चिल्ड्रन फॉरगेट दैट माइनस साइन एंड देन दे कम क्राइंग, सर वी डिड नॉट गेट मार्क्स, वी डिड नॉट गेट दिस, यू हैव रिटन रॉन्ग फॉर्मूला, हाउ विल यू गेट? So x2 when it is there, you delete second column. So when you delete second column, what you get? The first two rows are fixed, so here it is 4, 0, -2, -2. Now for the third case, you erase the column of x3. So column of x3, when you erase, what you get? 4, 0, 0, 2. Okay, 4, 0, 0, 2. This is what you get. So now we are in a position to write the eigen vector. So see this, x1 over, how much is it? Over 4, minus x2 over -8, x3 over 8, x1 over -4. Yeah, x1 over -4 we will get. In which one? What are you saying? Akash, there is some problem. One of the value is +2. Where +2? Yeah, sorry, yeah, it is plus 2. Correct. Yeah, plus 2. So this plus 2 will give us minus, yeah, minus will go away. Yeah, correct. Thank you for saving the answer. So this is what you get. I hope you are there, all of you. Let us quickly now go for solving this. So x1 over, therefore x1 over 4 na, you always simplify it to the reduced terms. Okay, don't write all terms because it will means don't scale it up. I would say this is x3, here x3 over 8. So when we now go further, so it is therefore x1 over 1, reduce the common factor, so x2 over 2, x3 over 2. Are you getting this? So this is the eigenvector. We are there, but technical mathematics, see, x1 below x1 is 1, x2 के नीचे 2 है, x3 के नीचे 2 है, आइगन वेक्टर 1 2 2 बनने वाला है. पर टेक्निकल मैथमेटिक्स के लिए यू राइट दिस x इक्वल टू x1 x2 x3. So what is the value for x1? If I equate it to t, then it is 1t. Okay, it is 1t means t. Then x2 is equals to 2t, x3 is equals to 2t. You just multiply 2 to this one, okay, and take t outside. Now when I take t outside, it is 1 2 2. Okay, and put t equal to 1, therefore capital X1. You can put t equal to 1000 also, there is no problem. You can put t equal to 5000 also, no problem, but all your answers are multiple of 1 2 2. So x1 is 1 2 2. This is your answer. Okay, are you getting this? Are you comfortable so far? I know I'm a bit slow on this, but first you get the uh, grip of the topic, then we can run ahead. You can try everything on your own. Now let us go for the next part. It is a distinct eigenvalue vector case, so it's not a difficult one. The difficulty arises when the case is repeated. That is the time the whole thing takes a turn. So we will see that after this example. But are you comfortable here? Please let me know yes or no, तो हम लोग आगे बढ़ते हैं. Otherwise कुछ doubt है तो पूछ लीजिए. You can ask me your doubts and then we can move ahead. Just tell me in the chat. Akash is there and there are few other students are there. Let me know whatever difficulty you are facing and then we can go ahead. Similarly, you are supposed to calculate for the second eigenvector also. Okay, so now we go uh, for eigenvalue for lambda 2 equal to 3 9 and 6 we had calculated, right? So lambda 2 is 9, so we now calculate for lambda 2 is 9, so we calculate a minus lambda 2I times capital X equals to O. So what is the matrix that will be formulated from the diagonal entry? subtract 9. So x1, x2, x3. What does this mean? This means that a minus 9I into capital X is O. This is what is the meaning. So you subtract from the diagonal entry 9. What do we get? We get here, my matrix is 7. 7 minus 9 is minus 2. 5 minus 9 is minus 4. And then 6 is the entry. 6 minus 9 is minus 3. All other entries will remain same, right? So minus 2, minus 2 and minus 2. Now we calculate the eigenvector by Cramer's rule. By Cramer's rule, what do we get? Cramer's rule, we get x1 here minus x2, x3. So delete the first. We will fix first two row and delete one by one columns. Okay, so first column, when we delete, we get 0, minus 4, minus 2, minus 2. Then when you do this one, delete second column, so you get minus 2, 0, minus 2, minus 2. And when you delete the third column, you get minus 2, 0, 0, minus 4. Okay, so x1 over how much we will get is minus of 8, minus of x2 divided by, we'll get here it is 4, right? Minus 2, yeah, minus 2 is plus 4, so that is there. X3 we will get 8. Okay, so again we reduce the common factor. So first we simplify, because there is that minus sign is there. Minus 8 here, x2 over minus 4, and here x3 over 8. So reduce it. So x1 over minus 2, then x2 over minus 1, and x3 over 2, and you call this t. Therefore capital X is equals to x1, x2, some error, wait a minute, yeah, x2, and then there is x3. और अब हमारा आंसर is ready. So minus 2t, minus 1t, and here there is 2t. So pull t outside. The moment you pull t outside, minus 2, minus 1 and 2. This is what you will get. Oh yeah, sure, I will do that. Yeah, we will do that. Okay, thank you. But on complex integration, Mr. Sandeep, we do have my playlist is already ready. The only thing is that in that I have not uploaded my more material on Cauchy residue theorem and Cauchy integral formula. That will soon be there, but we will also be live on that, because large number of students are in demand for that too. So we will have that too in the next session. Tomorrow, by the way, we are meeting at morning 8 a.m. to complete the last part of this topic, and this topic will be over. Okay, eigenvalue, eigenvector down and dusted tomorrow. Not much is there, because see, as far as the extent of the topics that I'm covering as per the Mumbai University syllabus. So you can also refer other syllabus, because almost same things are there, and those of other university students, if they are there, and if you have any other extra topics, let me know in the comment section. I would be happy to help you there on that topics also, because these topics are elementary version to the advanced mathematics. These topics itself are advanced, but there are more advanced topic where the world is actually working on, and we need to know those also. So there is something like orthogonal diagonalizations, and then quadratic forms, and etc etc. Then how do you take the geometry of the whole thing, and Gram-Schmidt process comes into picture, and many more things are there. So those we will see in the near future as we meet on more and more live sessions. So for time being, eigenvalues we are tackling. We will soon see complex integration also. Yeah, noted. Okay, Sandeep sir, noted about your request. We will go ahead now. So t is you put t equal to 1 and you get capital X2. This is our second eigenvector, that is minus 2 minus 1 2. Now see, I would like to tell you one again a very important instruction. Maybe you get minus 2 minus 1 2. Some another friend of yours can get an eigenvector as 2 1 minus 2. That is also correct. It is not wrong. It is just a multiple of this one. There is no need to get scared on any eigenvector. Okay, so this is our answer for x2. Now let us calculate the what we call x3. So for x3, I hope you all are comfortable till here. Please let me know how it is working at your end. Are you okay with this? And if you are okay, just hit like or just say that we are okay, and then we go ahead on the topic. या प्लीज़ जो भी है आपका सिचुएशन एट योर एंड, लेट मी नो कि समझ में आ रहा है कि नहीं आ रहा है, तो हम आगे बढ़ते हैं. Those of you are there, please let me know how it is working for you guys, and whether it is nice, easy, etc. Difficult also, I would be happy to help you. What is the difficulty? Let me know. Okay, faster pace. Let us go at a faster pace. So now for lambda 3 equal to what is the lambda 3 now? We have is 6, right? So lambda 3 is 6, then a minus lambda 3I operated on capital X is 0. So now what do we do is a minus 6I times capital X is O. So here you will get a minus 6I. So from the diagonal start subtracting 6. So you will get 1 0 minus 2 0 minus 1 and minus 2. Then there is minus 2 and 0. Okay, these are the values that you get inside your matrix, and then you have x1 x2 x3, and this is 0 0 0. Okay, and now let us go ahead. Here on this we shall calculate the eigenvector by Cramer's rule. So by Cramer's rule, you have x1 over the determinant of 0 minus 1 minus 2 minus 2 minus of x2 over 1 0 minus 2 minus 2, and then x3 over 1 0 0 minus 1. This gives you x1 over minus 2, then minus of x2 over minus 2, x3 over minus 1. So here you will have your eigenvector coming to be is it something is wrong? Is something wrong? Let me know. So yeah, minus 2 minus 2, is it correct? Yeah, fine. Here we have got this minus 2 minus 2 2 2 2. Yeah, so here we can get x1 over minus 2, here you get x2 over 2, here you get x3 over minus 1. Yeah, this is the thing. And now we can put x, capital X, you call this as t, so capital X is x1 x2 x3, and then you have as minus 2t 2t and minus t. So you take t outside, you get minus 2 2 minus 1. This is your eigenvector. So x3 is, you can put t equal to 1, so x3 is minus 2 minus 2 then 2, okay, and here you have minus 1. Okay, now they had asked us to find what is the concurrent, yeah, no, sorry, not concurrent, they had asked us to find the transforming matrix, right? In the question, as it is a lengthy question, yeah, so we had find the transforming matrix and the diagonal matrix of D, or we will also find what is the diagonal form. Okay, so these are the three vectors. So now write down, to find the diagonal form uh, and transforming matrix and diagonal matrix. So here we write, let P equal to capital X1 X2 X3. So P equal to x1 x2 x3. What is P then? We will have P with made up of all the eigenvectors that we have found. So the first eigenvector was 1 2 2, 1 2 2. Second eigenvector is minus 2 minus 2, oh sorry, minus 2 minus 1 2, and the third one is minus 2 2 minus 1. Okay, this is the eigenvectors we have got, and this is the matrix P which is there. Now this is P, and now we calculate P inverse also for this, and first we will calculate D also. Let D equal to, D is made out of lambda 1 lambda 2 lambda 3, and that is 0 0 0 0 0 0. So basically D is going to be, here it is 1 2, we, the eigenvalues that we had got, so the corresponding eigenvalues were 3, then there is 9 and 6, right? 3 9 and 6. So this is the diagonal matrix. This is what they ask. Now we check that. Now to check P D P inverse, so in the calculator you will need to calculate this 1 2 2 minus 2 minus 1 2 minus 2 2 minus 1. We need to calculate the inverse also, so we will calculate that. Let me know the inverse matrix in the in your chat box कि क्या आता है. So inverse we will need to calculate here. This you can do manually or you can do with the help of the calculator. So I'll be doing with the help of the calculator for all, like how it is working, and then we can get that. So the calculator will give us the answer for the matrix. I'll just but then there is we have 1, here we have 2, here we have 2. What is the inverse? Can you tell me the inverse quickly? Otherwise I'll be calculating from the calculator and letting you know. Here it is -1, here there is 2, and then there is -2. There is 2 and -1. Okay. Let me know what is the inverse you get. Is it must be coming 1/9 or something like that. Inverse we would need. Is it coming 1/9 as the first value? So yeah, 1/9 is common. Okay, so what do you get then? What is the inverse? Could you tell me row by row? I have calculated my inverse on this comes as 1/9 standing common, then you can write 1/9 outside completely. Yeah, second row. Okay, yeah, 1, yeah, correct. So 1 2 2, or you want me to write 1/9? Yeah, fine. 1/9, 2/9, 2/9, then -2/9, -1/9, then 2/9, and then there is -2/9, 2/9, and -1/9. Yeah, this is the matrix that we have. I'll erase this from here. And now see, in exam you will need to do this calculation. 1 2 2, 1 2 2 where? Well, 1 2 2. I have I don't get 1 2 2. Where is 1 2 2? Are you getting this? Yeah, first row is 1 2 2, second row is -2 -1 and the third row is -2 2 2. Yeah, correct. And that 1/9 is common for all. Yeah, fine. Now yeah, fine, got it. So we in exam, see now most of your teachers, how do they come to know, oh, whether you have done it or not? Because all this is now with your calculator, it is almost it's eradicated. That but I would still suggest you. Oh, just a minute. Just a minute. Okay, just a minute. Yeah. Ooh, ooh. Now I think there is some problem. The thing is gone away. Whatever I had written, yeah, is it there? It's gone away, and I have nothing with me now. Okay, fine, doesn't matter. So let just let us continue with that. This is the glitch that happens on, this kind of things keep happening. So our answer, when we write that PDP inverse, when we do, we get the answer here. PDP inverse will be the matrix here. Here it will be, you had 3, 9 and 6, right? 3, 9 and 6 for the eigenvalue and all, yeah. And here you got that matrix. Okay, so what you need to do in examination, let me tell you what you do in exam. First you multiply these two and write down the answer, so that at least your teacher knows, or your evaluator knows, that you have done the multiplication and you have explicitly done the whole process. Now see what is there is this portion, that, and finally you will get the matrix A back. Here it will be P inverse. This is P inverse value, those 1 by 9s and all. Okay, 1 by 9, 2 by 9, 2 by 9, and then there is minus 2 by 9, minus 1 by 9, and there is, in the second row is 2 by 9, then there is, third row is minus 2 by 9, minus 2 by 9, and here there is, third row is minus 2 plus 2. Okay, here it is plus, and here there is minus 1 by 9. So yeah, so having said that, you do the actual multiplication of this first two matrices and then write this, and at the end you write the final answer, that you get your matrix A back. So 7, 0, minus 2, minus 2, 5, minus 2, 0, minus 2, and 6. Yeah, this is the matrix you get A back. So finally, in have version control if PPT gets overwritten by mistake. Oh, thank you sir, on web version of PowerPoint. Yeah, Yeah, I'll keep that in mind. Thank you for that. I this was my it is not the web version, right? It's the one on the PC. I'll take care of that, because now see, whatever I had written, it is gone. No, doesn't matter, but it's there on the video, right? People got it. Fine, no problem. Now let us quickly take up a next question, in which the whole process is going to be, getting changed entirely. So now let us take up the next question, in which we will have repeated eigenvalues, and the things are going to change drastically, and it is going to be very different in the entire situation. So now let me take this matrix for a equal to 2 0 0 1 3 0 1 over here, and 0 and 2. Now we are taking this matrix A, and now the question is, first find the eigenvalues and eigenvector of A. Second, check whether matrix A is diagonalizable or not. And the third question will be, if yes, then find its transforming matrix, and its if yes, then find its transforming matrix and its diagonal matrix and its diagonal form. Okay, this is sorry, this is what we have to do. Now let us quickly do the thing. So answer, let ax, this is the most important step, let ax equals to lambda x, where x is not equal to 0. Determinant a minus lambda I equal to 0. Okay, so what does it give you? It gives you, here is determinant of matrix. Yeah, determinant of matrix will be 2 minus lambda, 3 minus lambda, and 2 minus lambda. From the diagonal, subtract the value lambda, and you will be getting this. Okay, now characteristic equation, can we write the characteristic equation quickly? Let us write the characteristic equation. So the characteristic equation here will be, again the follow the formula, lambda cube minus trace a lambda square plus m11 plus m22 plus m33 lambda minus determinant of a equal to 0. Therefore lambda cube minus the trace of this is going to be 2 plus 3 plus 2, so you have 4 and 7 lambda square. Then m11, what is m11? M11 is obtained by deleting the first row and the first column, so you get 6. Then next one is 4 minus 1 is 3, and then there is 6 again, right? Lambda minus determinant, the determinant over here how much is the determinant? Could you please calculate the determinant? Those of you are online, could you calculate the determinant and let me know how much is the determinant? I'll be waiting for your answer. So let's see. Those of you are calculating there will get the answer. So let me know what is the answer coming on the chat box. The determinant is 9. No, determinant is not 9. Oh, determinant is 9. Um, yeah, determinant is 9. Yeah, sorry. Yeah, determinant is 9 equals to 0. Yeah. So lambda cube minus 7 square plus 9 6. Yeah. So 9 plus 6 is 15 lambda minus 9 equals to 0. Now we will be going for calculation of, yeah, correct, lambda determinant is 9. Sorry, yeah, so it is 9. Can you calculate what are the eigenvalues? Yeah, and do mention here that is this is the characteristic equation is the equation. Yeah, eigenvalues are lambda 1 equal to, lambda 1 is 1, lambda 2 is 3, and lambda 3 is 3. Now see, here comes a, yeah, correct, absolutely correct. So here comes the most important thing, algebraic multiplicity concept. So we had seen what is algebraic multiplicity. Algebraic multiplicity of a particular eigenvalue is the number of times it is repeated. So here we write here that algebraic multiplicity in short it is written am, okay, am of lambda 1 equal to 1 is 1, okay. Then algebraic multiplicity I'm for time being I'm writing like this, am of lambda 2 equal to 3 is sorry, lambda 2 equal to 3 is 2. This is what we have. Now see, here looking at the eigenvalues we cannot conclude that whether the matrix is diagonalizable or not. This leaves us into a problem that we will need to go a longer way. There is no shortcut way now to tell whether the matrix is diagonalizable or not. Then only option that we are left is to do the long cut method. So what is long cut method? The long cut method is that we need to calculate the eigenvalue and eigenvector in a different manner. The eigenvectors are to be calculated in a different manner. Now see how it is done. Now this is slightly lengthy. Those of you are new, okay, or those of you are from direct second year, or you are absolutely new, hold on for some time. This is done for you children in the previous semesters when the concept of rank and system of linear equations was introduced, so that knowledge will be used here. So let us see how to do. So first we write for lambda, we have got lambda 1, right? For lambda 1 equal to 1, we go for finding eigenvector a minus lambda 1 I into capital X equal to 0. Okay, now we need to find something called as geometric multiplicity. For this we cannot now use Cramer's rule, so I'll just put again a word of caution. So a word of caution, do not use Cramer's rule. Do not use Cramer's rule when eigenvalues are repeated eigenvalues are repeated, especially while showing matrix is diagonalizable. Okay, eigenvalues especially while showing matrix, I'll just take this, especially while showing matrix is diagonalizable. Okay, this is a word of caution. So again, a danger sign here, so I'll have this, not to use this, very important. Do not use Cramer's rule. You can use Cramer's rule when, I'll tell you, the after this example getting completed, I'll tell you this very important thing is there. Don't use Cramer's rule when and when to use. So right now we are not going to use Cramer's rule because we are in a very special case, because we are showing the matrix as diagonalizable, or we are actually checking whether it is diagonalizable or not. So whenever you do this check, you don't use Cramer's rule. So what to use? So we have to use now something called as method that was taught in previous semesters during rank. So first thing, a minus lambda I we write here. So the matrix that we will get when you have this thing, so it is a minus I into capital X equal to 0. So here what is it? It is 1, 2, and then it is going to be 1, 0, 0, 0, 0, and here it is 1, and here it is 1, right? We got this. So x1, x2, x3, and then there is 0, 0, 0. This is what we have got. Now we go for further thing, that is x1. Oh sorry, wait, sorry, we will go here. Now comes the main part, what to do and how to handle. So here you need to do this step. We will be finding the rank of this matrix. Okay, we will be finding the rank of this matrix using row echelon method. So using row echelon method, when we do, okay, when we use, we now find rank of a minus I using row echelon form. Okay, now when we use row echelon form we are allowed only to use row transformation. So what are they? Let us see. So our we have to remember while making row echelon form, the first thing is that this entry a11 should not be equal to 0, or if it is equal to 0 then there are special case, but right now in our setup we remember that it should be either 1 or a non-zero number. So a11 entry, the first entry should be either 1. If it is 1, very good. If not 1, then it is, remember that it is a non-zero number. Using that a11, make all other entries below it 0. This you make 0. So r1, r2 entry, this is 0. So we will be now using r3 changing to r3 minus r1. क्या करेंगे हम लोग? क्या करना है इस टाइम पे ध्यान रखना है कि a11 जो एंट्री है, द फर्स्ट एंट्री, वो ज़ीरो नहीं हो सकती. ज़ीरो है तो बाद में बहुत गफला हो जाता है, तो उसको जाने दो. हम लोग को ये ध्यान रखना है कि वो नॉन ज़ीरो एंट्री है. 1 है तो बहुत ही अच्छी बात है. फिर वो एंट्री का यूज़ करने के बाद, वो एंट्री को यूज़ करके हम बाकी सारी एंट्री उसके नीचे जो है उसको ज़ीरो बनाएंगे. तो अब यहाँ पर क्या मिलता है? ज़ीरो के जगह पे ज़ीरो है ऑलरेडी. 1 के जगह पे अभी ये जो थर्ड एंट्री है ना, उधर हमको ज़ीरो बनाना है. तो हाउ डू वी मेक दैट? वी यूज़ रो ट्रांसफॉर्मेशन. वाई रो ट्रांसफॉर्मेशन? बिकॉज वी आर डूइंग रो इचेलॉन फॉर्म. रो इचेलॉन फॉर्म में केवल और केवल रो ट्रांसफॉर्मेशन ही लगता है और कुछ नहीं. We can use only row transformation now. So here it is 1 0 1 0 2 0, and now what is the next one here? It is 0 0. Now see, 1 minus 1 is again 0. So here it is this x1 x2 x3 0 0 0. Okay, we have got our row echelon form we have obtained. Okay, this is row echelon form. So here we write now, write this thing. Here we write rank of a minus I is number of, or we just write directly, we'll write direct rank here. See, what is the rank of a minus I? It is the number of non-zero rows in that matrix. So how many non-zero rows are there? The first row 1 0 1, it is a non-zero row. Second row is 0 2 0, so this is also non-zero. So the first two rows are non-zero, so rank is 2. How many unknowns are there? Unknown, n is the number of unknowns. So n being a number of unknowns, or you can also treat n is the order of the matrix. Okay, in our case it is fine, n is the order of the matrix. So n is 3. So number of free variable is equals to n minus this rank, n minus rank of a minus I. This is there. So n is 3 and this is 2, so this is 1. So one variable is free. We will see that. Also geometric multiplicity, this is here. Also geometric multiplicity of lambda 1 equal to 1. What is this? This is the most important concept. You have to remember that it is, I gave you the formula in the beginning of the series, the beginning of the stream today, that it is n minus rank of a minus lambda I for that particular lambda I into capital I for that particular eigenvalue lambda I. So for lambda 1, the geometric multiplicity of lambda 1 equal to 1 is same, the number of free variable, it is n minus rank a minus lambda I, that is, we had written this as n minus r, so here it is 3 minus 2, which is 1. Now here this is the most important concept. Now we go for simplifying for eigenvector. How to simplify for eigenvector? Let us see that. So what do we get from the first two equations? So here I get x1 plus x3 equal to 0, and another relation I have got is 2x2 is equal to 0. Okay, so x2 has no other option. X2 has no other option other than saying that from these equations, what do we see? X2 is definitely 0. There is no option in this for x2. But from the other part over here, we also get to know that x1 is same as minus of x3, right? Sorry, I'm extremely sorry. So do you get that x1 is equal to minus x3? x1 is minus of x3. Do you get this? Because this is the time when you are finding eigenvector in a very different manner. Following, hit like or let me know that you have followed. Yes. Okay, so now we go for the general formula. What is the general formula of eigenvector? Eigenvector looks like this. Eigenvector is x1, x2, x3. Eigenvector being x1, x2, x3, what do we got about x1? We got that x1 is same as minus of x3. Correct? We got this. What do we got about x2? x2 we straightforward we got it is 0. No problem only for x2. What do we got about x3? We got nothing. x3 is nothing we got. Now you come to know what is the meaning of a free variable. What is that free variable? See, we said number of free variables. You can write free variable, but here we got 1. Number of free variables is 1. So out of 3 variable, 1 variable is free. 1 variable is free means he is independent of anything. He doesn't want to come into the picture. So what is that? Rather, that means everything will work according to that variable. So here that free variable is x3. Can you see there are 3, x1, x2, x3. Now only main variable has become x3. That is why x3 is called a free variable. And here x3 when you pull outside, you got minus 1, 0, 1. Okay, and now you say put x3 equal to 1. Therefore your first eigenvector x1 has become minus 1, 0, 1. This is what has come out. Got this? This is my first eigenvector, and we also found the geometric multiplicity. This is how geometric multiplicity of a particular eigenvalue is to be found. Now let us go for the next one. The next case is extremely important because we are going to handle the repeated eigenvalue for the first time. So repeated eigenvalue we are handling. The eigenvalues we had got were 1 3 3, right? So now we check. Yeah. So yeah, thank you very much. We have here now we write down for lambda 2. अभी देखिए लैम्डा 2 तो 3 आया है, लैम्डा 3 भी 3 आया है, बराबर ना? तो एक तीर से दो निशाने ये करना है। ये केस थोड़ा अलग है, एक तीर मारेंगे दो आंसर निकालेंगे हम लोग इधर, ये बात है। दिस इज हाउ इट इज। इसमें कोई ये मतलब लॉजिक तो काफ़ी अच्छा है, काफ़ी स्ट्रॉन्ग लॉजिक है इसमें। पर अभी हम देखते हैं कि एक ही प्रोसेस करेंगे दो आंसर कैसे निकालते। चलिए देखते हैं। सो व्हाट डू यू डू हियर, a माइनस लैम्डा 2i into capital X is equals to 0. So basically a minus 3i into capital X is equal to 0. ये बात हो गई। अब इसके बाद में हम क्या करेंगे, अब हम मैट्रिक्स लिख देंगे। हमारा जो मैट्रिक्स था, क्या आता है हमारा मैट्रिक्स? हमारा मैट्रिक्स आता है डायगोनल में से सब्ट्रैक्ट कर देते हैं 2 को। तो डायगोनल में से 2 को सब्ट्रैक्ट करने पे क्या मिलेगा? हम नहीं सॉरी 2 नहीं, सॉरी नॉट 2, 3 को सब्ट्रैक्ट करेंगे। तो डायगोनल में से 3 सब्ट्रैक्ट करने पे हमको मिलेगा 2 minus 1 we get is minus 2 minus 3 minus 1 0 and 1, 0 minus 3 sorry 0 तो ऐसे ही 3 minus 3 0, here it is 0, then 1 0 and 2 minus 3 again we get minus 1. ओके, x1 x2 x3 और ये है कैपिटल x 0 0 0। बस ये समझ में आया? ओके, थोड़ा सा ध्यान से करो, ये मैट्रिक्स आपको पता चल गया तो आपको पूरा आंसर मिलेगा, बराबर। अभी यहाँ पर खास बात क्या है, वापस हम लोग क्या करेंगे, रो इचेलॉन फॉर्म का मेथड यूज़ करेंगे और रो ट्रांसफॉर्मेशन लगा के रैंक निकालेंगे। तो रैंक कैसे निकलेगा? R3 चेंजिंग टू R3 प्लस R1 करो। ओके, हमको क्या करना है, मेरे को तो यहाँ पर नॉन ज़ीरो नंबर चाहिए ना, फर्स्ट एलिमेंट नॉन ज़ीरो होना चाहिए। तो फर्स्ट एलिमेंट नॉन ज़ीरो और उसके नीचे सारे ज़ीरो बनाने हैं। तो ये आ गए ज़ीरो, ये भी आ गया ज़ीरो। इसको ज़ीरो कैसे बनाएंगे? 1 को ज़ीरो बनाना है यूजिंग द फर्स्ट एलिमेंट, तो आप ऐड कर दो। तो अब हम क्या करेंगे यहाँ पर -1 0 1 एंड देन थर्ड रो में क्या होगा, सेकेंड रो में तो कोई चेंज नहीं है ऐसे ही। तो फर्स्ट रो को थर्ड रो में ऐड कर दो तो 0 मिल गया, 0 प्लस 0 वापस 0, ये भी 0। ओके, तो ये मिल गई x1 x2 x3, तो ये 0 0 0 ये आ गया है, ठीक है। अब रैंक बताओ, रैंक क्या होती है? रैंक होता है नंबर ऑफ नॉन जीरो रोज। सो रैंक आर रैंक ऑफ a माइनस 3i। ओके, a माइनस 3i की रैंक क्या हुई? सॉरी, a माइनस 3i की रैंक, व्हाट इज द रैंक? इट इज 2। rank is 2, no sorry, rank is 1, number of non-zero rows, yeah, 2 non-zero rows are there in front of us, the bottom 2 zero rows are there in front of us, so rank is over here this -1 0 1, that is a non-zero row, rank is 1. Thank you Akash. So now, and n is number of unknowns. Unknowns are how many? 3. So number of free variable is n minus r, right? N minus r is 3 minus 1, which is 2. So that means now two variables are free. How do we get that? Let us see. Two variables are free. And what about gm? Gm is also 2. Number of free variables is nothing but gm. Okay, so we write here, therefore geometric multiplicity of lambda 2 equal to 3 is 2. Okay, please write down like this, in bracket, lambda 2 equal to 3 is 2. Like this you write, it makes good sense. Otherwise lambda 2 equal to 3 ho jata, something like that. So please be very careful with the English. Okay, now we will calculate how the vector is coming. This is very first time you are doing here, so we go for this expression, this matrix. Check this matrix carefully. Okay, what is the output from this matrix? What do we get? We get only one equation. What is that equation? That equation will be minus, here I am just writing for some time, minus of x1 plus x3 equal to 0. This is only one equation you get, right? Rest other things all are 0. So we will write here, now we have got minus of x1, we have got minus of x1 plus x3 is equals to 0. Therefore minus x1 is equals to minus x3. Therefore x1 is x3. Okay, but what about x2? We did not get anything about x2. When you don't get anything like this, that means also x2 के बारे में कोई जानकारी ही नहीं है, मतलब x2 फ्री घूम रहा है, right? x2 is already become independent from the process, so x2 is x2. Now you will come to know that why there are two variables free. See, so therefore capital X, now we write the formula, capital X is equals to x1, x2, x3, right? So x1 has become equal to x3, x2 has remained already independent from the process, only it became independent, that it is saying x2 is equal to x2. And what about x3? x3 is also x3. We have expressed x1 in terms of x3. Don't write x3 again x1, so you will get nowhere. Okay, so here you understand that x2 and x3 both are free variables. In this formula you come to know now that x2 and x3 are free variable. How many of you have followed? Raise your hand and let me know. If you have not followed, then I'll try to re-explain otherwise. Have you followed this? x2 became x2. Okay, fine. Anybody else who is there, who has any difficulty? Followed. Fine. Okay, cool. Thank you. Now we go for the next part. Now मैंने बोला था ना, एक तीर से दो निशान है. So you are going to just see the magic of maths, I would say. This when I was in college, I was very surprised with this thing. Wow, this is like a vision I felt, but then very nice way it is. See this, uh, x3 can be written as x3 is alone, right? But I want to write it along with x2. So how do I write 0 x2 plus x3? That x3, the first variable x3, I can now write like this. x2 is already alone, so I want to write along with x3, so I write it x3 like this. Now x3 is alone again, right? So I write it as 0 x2 plus x3. Now see, this magic which you saw, it is now what I can tell you. Try to see this as addition of matrices, addition of two matrices. So what you do, this will be 0 x2 x2 0 x2 plus x3 0 x3 and x3. So take x2 outside. When you take x2 outside, you get 0 1 0 here. Then you see x3, and then here it is here it will be here it will be 1 0 1. Okay, now I said, you see, we solved the whole thing only once and we got two answers. These are our two vectors x2. So therefore eigenvector for lambda 2 equal to 3 is, right, lambda 2 is 3, right? Lambda 2 equal to 3 is x2 equal to 0 1 0 and x3 equal to 1 0 1. These are the two eigenvector that you can get. Sorry. So I hope you followed this. So these eigenvectors are now going to serve the purpose. So we now write, now comes the main crucial understanding regarding whether the matrix is diagonalizable or not. So we now conclude that part also. So we write here, see, in our starting here we wrote that these are algebraic multiplicity of lambda 1 is 1. So you can label this as the first equation, okay, number 1. This you can label as number 2. You can label here that geometric multiplicity was 1, so you can label this as number 3. Here we found geometric multiplicity is 4, yeah, lambda 3 is 2, so you label this as 4. So we now write here that from 1 and 2, no, from 1 and 3 we get am of lambda 1 equal to 1 is equal to gm of lambda 1 equal to 1. They are same. From 2 and 4 we get here am of lambda 2 equal to 3 is equal to gm of lambda 2 equal to 3. Hence matrix A is diagonalizable. Got this? So this is the place the problem becomes lengthy. Okay, because we had to find everything. You cannot write in short and sweet words that it is diagonalizable or not. We have to do the full checking till AMGM. Okay, ये आपको समझ में आ गया? तो for doing this much you will get your 6 marks if it is just to check whether the matrix is diagonalizable or not. So this is all lengthy process. You have to get used to this, and this is how manually it is done. कोडिंग में तो क्या है, कोडिंग में तो फटाफट आंसर आ जाता है. इफ़ यू हैव अंडरस्टूड दिस प्लीज़ हिट लाइक, एंड नाउ वी गो फॉर द नेक्स्ट पार्ट, finding the diagonalizable form and everything. So now P is, see, the matrix P has two different names. The two different names are, first name is transforming matrix, or sometimes it is called modal matrix. Now also remember, I have given over your notation P. Some people like to give notation M for modal matrix. Okay, but what I have given is standard across the globe. M is also used some places. You just have to be flexible with the notation. Okay, no problem, but just be little bit flexible with that notation, because sometimes some people use it M, some people use it P. I use it P over here. So P is the modal matrix, also another name. So P formulation is capital X1, capital X2, capital X3. So what do we get from capital X1? Capital X1 was -101, -101. Capital X2 is 010, 010, and this is 101. Okay, fine. So these are the eigen vectors, and then you have formulated the matrix P over here. Are you getting this? Alright, this is what you get. Now we go for finding the diagonal form D. Diagonal D is basically lambda 1, lambda 2, lambda 3. So it is basically going to be on the diagonals, right? So it is 1, 3, 3 on the diagonal, and this is the diagonal matrix. D is the diagonal matrix. Okay, I'll write here diagonal matrix. Now after this we will need to find the diagonal form. So diagonal form is PDP inverse. We have to check and show is PDP inverse, and this has to come equal to A. So let us calculate quickly. P is here, D will be this. So PDP inverse -101, 010, 101. D is 133, 0 0 0 and 0 and 0 and 0, and P inverse. Now let us quickly calculate this P inverse. I'll do on my calc. Yeah, so it is here I am getting -1, -1, and then here I have 0, here it is 1, here it is 1, and then 0, here it is 1, okay. What is the inverse of this matrix? Do you get any inverse? Do you get the inverse? Could you tell the inverse? I have got the same matrix as the inverse. Are you getting the inverse, guys? Are you there? Calculate the inverse and just write down the first. Is it coming the same? I'm getting the same answer. The same matrix is the inverse. So just a minute. Are you getting any different? Half. Okay. Let me check. Yeah, I'm not getting. Could you please tell me the answer? Are you getting this? Minus half. Okay, so there is half here and then there is half. What about the next one? 0, 1, 0. Okay, and then there is half. Okay, fine. I was getting the same answer. I don't know, my calci may be some mistake. Okay, fine. So let us multiply them. Check the multiplication. Do you get A again? Do you get the matrix A back? I think P inverse. Akash, you're just check, because I think P inverse is P itself. So I am slightly dubious about that answer. Just check your answer. I'm not sure right now. Can you tell the answer? Others, anybody who has done the calculation, check your answer. Okay, so here the answer is I cross check the. Okay, fine. Can you multiply and get the answer A back? Do you get that answer? So we will need to do the multiplication now. So it is, this is minus 1. Okay, and then there is 0 here, then there is 3 here there is 1, here there is 0, here there is 3. Okay, then here there is 1, here there will be 0, and here there will be 3. This multiply with the inverse and check. here it is minus 1 0 1 0, here it is 1. Yeah, anybody else who is calculating along with him, please let me know what is the answer. Let us know how it is getting through, and then we can go ahead. 0 and okay. I guess Akash, your answer isn't coming correct. The answer of the uh, same matrix inverse is same itself. Matrix as answer. Inverse, I am not sure with the inverse, because the inverse is the same matrix back. Inverse, P inverse are, please check with the P inverse. It is not coming half. The matrix is orthogonal, so P inverse is P itself, P transpose. You will get the same matrix again. Just have a check on this. Okay, otherwise we'll just see minus half 0 1 by 2 0 1 0 half 0 1. I think this answer, Akash answer is right. Okay, Akash's answer is right. Okay, fine. Let's do this. Then are we getting A back? Okay, let's see. Minus 1 and 1 is half. Here it is 3 by 2 plus 3 by 2. Okay, we are getting 2. That is fine, good. And then there is this, so this is 0. Here it is minus half plus 3 by 2. Here it is the first column is, yeah, so here it is minus half, getting same, but I think there is a mistake then. I think there is some mistake is there then. Where did the thing go? Keep just a minute. But the thing is not coming, right? Yeah. Yeah. Okay. Just check, are you getting A matrix back? I am not getting A matrix back. Yeah, I want that way. I think there is some mistake is there. 1 0 minus half, and then there is some error is there. Are you getting the same matrix back? A matrix as answer. Okay, we are getting. Yes, getting A, fine. But I doubt P inverse. Determinant, is it 1? How that 1 by 2 came? I am not getting 1 by 2 as the answer. See this, with this answer, when you multiply this 1003 1 over here, when you will multiply, this is second row first column, that you get 0 here. This is second row first column, here you must get 0. Then just check the multiplication. You need to do the manual multiplication all the time and check, because if it is wrong, then it won't work out at the end. Okay. This is 1. You need to do the multiplication also. So this is 1 0 minus 1, this is 0 3, this is 0, this is 3, then this is 0, here it is 0. Okay, 0, and here it is 3. Okay, here it will be 3, and then 0, here it is 3, here then it is 0 over here. Here it is 0, and here it is 1 into 0. Just a minute, I think there is some error is there. This all is not going only. Oh yeah, just a minute. Diagonal form is diagonal form of A is PD P inverse. A is minus 1 0 1 0 have a check on this. The eigen vector that we got, there is something is wrong, I think. Oh yeah, this is here 1 0. Okay, fine. You calculate and you must get A back here. So minus 1 0 1, and then there is 1 0 1 1 0 1, and your eigenvector is 1 no 1 3 3 1 3 3 0 0 0 0 0 0, and you calculate P inverse here, and you must get capital A back at any cost, otherwise there is not P into D. Yeah, so you must get capital A back over here. 2 0 1 0 3 0, and here it must be 1 0 2. So this is your matrix back, and this is the diagonal form of A. So this is all about on this. Now very important thing comes into the picture here, is that whenever you have the eigenvalues repeated, I wanted to give you this word of caution, how when to use Cramer's rule and when not to use Cramer's rule. So first thing, caution and important note, it is note when to use Cramer's rule. So first thing, if eigenvalues are distinct, use Cramer's rule find eigen vectors. Second, if eigen values are repeated, say lambda 1 is 1 and lambda 2 is 5, then for lambda 1 equal to 1, which is distinct, we can use Cramer's rule to find eigen vector. But for lambda 2 equal to 5, we cannot use Cramer's rule. Okay, we cannot use Cramer's rule. This is the main thing, double colon. Sorry. Now the third thing is, there is one more here. Suppose lambda 1 is 1 and lambda 2 is 5, and we have to show that matrix, we have to show or check that matrix is diagonalizable or not, then we cannot use Cramer's rule to find eigen vector. Okay, again over here cannot has come, please be very careful. Okay, so I have tried to give you the general. Good afternoon, a very good afternoon to you. So this is the general overview of when to use Cramer's rule and when not to use Cramer's rule. When to use Cramer's rule: eigenvalue distinct, free to use Cramer's rule. Eigenvalues are repeated and they have not told whether to show it is diagonalizable or not diagonalizable, then for the eigenvalue which is distinct you can use Cramer's rule, but for the repeated one you cannot use Cramer's rule. And if the question says show that the matrix is diagonalizable and your eigenvalues come repeated, then you are forced to use the row echelon form. Okay, thank you so much, God bless you. Crystal clear हो गया है तो I am very happy. It serves the purpose. और lambda show that का टाइप आया कि शो दैट इट इज़ डायगोनलाइजेबल, तो उस टाइम पे अगर आइगन वैल्यू रिपीटेड है तो क्रेमर्स रूल यूज़ करना ही नहीं है. not to use Cramer's rule because हमारा आइगन वैल्यू रिपीटेड आया है, हमको ज़बरदस्ती AMGM निकालना पड़ेगा. ठीक है, तो ये बात है. सो दिस इज़ ऑल अबाउट the Cramer's rule, when to use, when not to use, and diagonalization. Okay, now there is one more thing is there, we will see all that things tomorrow. Thank you for joining in. If you want some practice questions, I'll give you some practice part so that you can try it on your end on repeated eigenvalue, and you can check the same questions you can throw on them also. Find eigenvalue and eigenvector for A, which is 2 minus 1 1 minus 1 2 minus 1 1 minus 1 and 2. This is A, and you can do for and also check whether it is diagonalizable, and similar also do wait, I'll give you again a question only better. You can do for this one too. This is also a good question where you get repeated. See, you need to practice for the repeated case, and that would be a very good thing. I'll give you somewhere repeated eigenvalues land up that would serve the purpose of the whole lectures. So A is 6 minus 2 minus 2 2 3 minus 1 minus 1 and 3. Okay, same question as above. Okay, thank you for joining in, and this is all I have from my side. If you have any doubts, please do revert to me in the chat box, or you can let me know. We are done with the today's series. It was from 11 to 134. Okay, so thank you for staying there, and yeah, this is all. If you have any doubt, let me know. I'll be happy to help you, and anything more you want on this topic, let me know in the comment section, or you can contact me. Thank you. So we shall stop now, and I hope you have understood the topic. Like and share and subscribe, please do that. Okay, so and please share it with maximum of your friends from other colleges also, so that they also benefit. And if anybody, like, who is lagging or who has a backlog, they can also refer this. Do share with everybody. Thank you all. So we'll stop now, and we'll go ahead. So see you tomorrow. Thank you.